Yeah, cool. So I'm Yingbo, and I'm the lead developer of Modeling Toolkit and the DigiWell compiler. And today I will talk about scaling equation-based modeling to large systems through loop rerouting. And I'm kind of curious. So in this group, how many people are already familiar with the concept of a-causal modeling or equation-based modeling? Can people just talk in the chat or raise their hand? Hold on, I can't click it.
It is familiar with casual or accasual.
Yeah. Sorry, I was taking watermelon. Yeah, I worked with Modelica, and some of my colleagues have worked with Modelica also.
Okay, cool. So yeah, so because sounds like people are quite familiar with ACOS modeling already, so I'll be pretty quick in this section. So yeah, so the difference between causal and a-causal modeling, I want to use the RC circuit and the RLC circuit to demonstrate their difference here to the modeler, and then we will talk about how the compiler works a bit later. So when people need to implement a RC circuit for a causal modeling framework, they need to list all the conservation laws. So Kirchhoff voltage law and Kirchhoff current law, and all the device equations. So in this case, we have a resistor and a capacitor. So we list all the Ohm's law, and we say that the voltage change of the capacitor is proportional to the current of the current through the capacitor, right? And from all these four equations, we know that there's only one differential variable, right? Only one differentiated variable. So this variable must be the state. And we want to solve this variable in terms of its non-differentiated part, right? So the voltage of the capacitor. And after manually solving this differential variable, we get a differential equation, the ordinary differential equation in this case. And because we see that there is one derivative and one subtraction and one division, so we know that we need to use a integrator block and the add block and the gain block, right? So after we identify all these elements, we draw such block diagram. And in here, on the right, we can actually implement causal models in Modeling Toolkit as well, right? So we have the integrator block, the add block, and the gain block. So in here, I'm just adding a voltage source to make that a bit more interesting to simulate it. And we need to connect all these blocks together in just like in the block diagram on the left. And then we will finish building this by calling Julia system in Modeling Toolkit. However, with a causal or equation-based modeling system, all we need to do is to instantiate physical models. So in here, we know that we have a resistor, a capacitor, and a voltage source. And we want to describe what the voltage source looks like. And of course, we need to have a ground so that the solution is unique, right? And after instantiating all these physical blocks, we just need to connect them in the right order. So we are connecting the positive terminal of the voltage source with the positive terminal of the resistor, and the negative terminal of the resistor to the positive terminal of the capacitor, and so on and so forth. And one thing to note is that we must connect a ground, right? Otherwise, the a-causal framework will just give you an error and saying that this system is underdetermined. And what happens if we introduce a inductor element? With the causal modeling framework, we must rederive all the equations again from the conservation laws and device equations. So in here, the conservation law is pretty trivial, but in the device equations, we need to introduce the inductor equation, which is saying that the change in current is proportional to the voltage across the inductor. And in here, because we have two differentiated variables, we know that there must be two different ordinary differential equations for that describes the system, right? And after some algebraic manipulations, we got these two simplified ODE systems. And because there are two derivatives, we have two integrator blocks, and these are the I block, and we have a gain block. No, we have two gain blocks. So in here, it's pretty straightforward to translate this block diagram into modeling toolkit model. And we just need to connect, after instantiating all these blocks, we just need to connect them the right way. And this process probably takes a human about 15 minutes to make sure that they have done it right. And with a causal framework or a causal style of modeling, it's pretty time consuming that just adding a simple inductor, it will require a complete rederivation from people. But with a causal modeling, all we need to do is to instantiate a new inductor and connect the inductor between the resistor element and the capacitor element. And it takes about only 1 minute of human time to modify this system, right? So again, to recap, this is how the block diagram evolves when we introduce a new inductor, and it looks completely different. However, with the acausal modeling, all we need to do is to introduce a inductor model. And the code for the causal model involves from coding on the left to code on the right, right? So the code on the right looks completely different from code on the left, from just adding a simple modification to the circuit. And and just to reiterate, adding an inductor, a causal modeling framework just requires instantiating the physical model and connect them properly. So a simple modification in the physical model corresponds to a simple modification in the computer model if we are using the acausal modeling approach. So that's the power of acausal modeling approach, right? But the drawback is that all the work of compiling these physical models into a causalized model like this completely lies to the it is completely done by the compiler, right? So every time when we are instantiating a new model or simplifying a new model, the compiler needs to analyze every single equation in this system, and it works pretty well and for small systems, but it wouldn't really scale to a larger system where, for instance, in at Julia Hub, we have developed battery models where we know that some battery engineers want to simulate 1,000 battery cell models, and if we simply repeat 1,000 battery cell models in modeling toolkit will just not even compile. We will not even finish compiling that model. So so let's talk about DigiWell compiler, which is a accelerated modeling toolkit backend. So DigiWell compiler solves this problem by a technique called loop rerolling, and I'll talk about that later. So first thing first, the way to use DigiWell compiler is just to load DigiWell compiler in the Julia programming language, and just like MTK, we need to call structure simplify. But just before structure simplify, we only need to add a IR system call to convert a modeling toolkit system to a system inside DigiWell compiler. And all the other code should be more or less the same. And the point here is that just with 2 lines of change, we can enable enormous scalability improvements. So the loop rerolling I'll talk about loop rerolling technique here in more detail with the model example of a RC ladder. So in here, imagine we are connecting RC elements in this way, in this repeated way, and it's repeating n times. In here, to take advantage of the loop rerolling transformation in DigiWell compiler, we must, in the front end, instantiate this model in batch, meaning that we need to communicate to the compiler that we are instantiating a resistor, the same resistor model n times, right? So all these resistors only differ by name, and all their equations and variables have completely same structures. And so, and this is also the case with capacitor, because if we don't communicate this information in the front end, rediscovering this information inside the compiler is way too hard. It will become a subgraph isomorphism problem, and I think it's NP complete. So, maybe it's not NP. Is it NP complete? But anyway, it's a pretty hard computer science problem, and we don't really need to solve that, right? Because the modeler knows that they are repeating the model n times, so we don't really need to rediscover this kind of repeated structure on the level of equations. So if we just simply expand that this previous model, we'll see equations like these. And if we take a closer look, we can see that the first equation and the fifth equation look basically the same, other than the variable names, right? So in the first equation, we have resistor 1V, and in the fifth equation, we have resistor 2V. And in the first equation, we have resistor 1PV, and in the fifth equation, we have resistor 2PV. And in the first equation, we have resistor 1NV, and in the fifth equation, we have resistor 2NV. And the same thing also happens for the second equation and the fourth equation, right? So we have resistor 1PI, and resistor 1NI. And here we have resistor 2PI and resistor 2NI. To capture this repeated information, we use a data structure called the variable classes and equation classes. So in here, we are saying that resistor 1V and resistor 2V are variables with different names, but they have the same purpose, right? And that this is also the case with resistor 1PV and resistor 2PV. And in here, we also have equation classes where we canonicalize all equations into equal to 0, right? Otherwise, it's a bit too flexible to manipulate in the compiler. So in here, we are just saying that the first equation has the form of x minus the difference of y and z. And the second equation has the form of 0 equals to x plus y, right? So the first equation and the fifth equation are they are both in this first equation classes. And the second equation and the sixth equation are both the second equation class, the second equation classes. And just getting the equation classes and the variable classes information is not enough for loop rerolling, because in A-causal modeling compilers, in the last stage of the compilation step, we need to order all the equations in a way that can be evaluated by the compiler, right? By the computer, right? So before we use a variable, the variable needs to be already defined, basically. So that's a topological sort. That's a topological sorting problem. And if we order equations in this particular way, it's trivial to transform this list of equations into loops. So in here, v11 just denotes the first variable from the first variable classes, and v12 denotes the second variable from the first variable classes. So if we have structures like this, we can trivially reroll them into loops. And in here, the right, we are basically calling f 3 times and writing the result into VS into some particular indices into the VS vector. And this is how we save variables like v11, v12, and so on. And currently in JSON compiler, we don't quite guarantee that we are doing this process optimally. And I'm not sure if optimal topological sorting into loops is even a polynomial time can even be done polynomial time in polynomial time. So we are just doing a greedy approach. And I think the greedy approach in practice works reasonably well. So in here, with 100 RC elements, where n equals to 100 in this case, we will get back a loop of length 97. We don't get 100 because there are boundary conditions, right? So, and also, as I mentioned earlier, the loop rerolling process, because of the topological sorting problem, it's not always done optimally. So sometimes we don't, we miss a few iterations, and that tends to be okay in practice. So I motivated this problem with battery models, right? So in here, I want to demonstrate the example with loop rerolling on a dual-sim battery example, where this model is a single particle model of lithium nickel manganese cobalt oxide battery cells. And in here, we can see that without the blue line is with no loop rerolling, and the y-axis is the compile time, and the x-axis is the number of cells in this battery model. We can see that without loop rerolling, the compilation time is scales quadratically, and it's intractable to even simulate 1,000 battery cells, right? But with loop rerolling, in this regime of 1,000 battery cells, the compilation time scales almost linearly, and we can comfortably even compile to 5,000 battery cells, which only takes about 1 minute if we see the y-axis. And of course, we want to compare the results. And we can see that the solution of the scalar by the scalar compilation process and by the loop rerolling process are completely the same. And for the remainder of this talk, I want to talk about a few new transformations that we have done in JSON compiler, and also some of the future directions of JSON compiler and modeling toolkit. So the first transformation that we have implemented in JSON compiler that is not yet implemented in modeling toolkit is inline linear solver optimization. This is an optimization that is extremely important for basically all multi-body models. So the simplest multi-body model, of course, is just a single pendulum. And if we implement a single pendulum model in the Cartesian coordinate in modeling toolkit, we will get the simplified model, the simplified equations like this, where not only we have two differential equations, we also have two algebraic equations. And we all know from the first year physics class that we only need angular position and angular velocity to describe the pendulum. So why would modeling toolkit give us a simplified system with two more equations? Well, if we take a look at this two algebraic equations more closely, we can see that the algebraic variables are lambda and angular acceleration, and they always appear linearly in these two equations. So in here, lambda is linear in this term, and angular acceleration is linear in this term, and there are no other algebraic variables in this term. And for the second algebraic equation, we see that there is this angular acceleration in this term that appears linearly, and this lambda term, this lambda in this term appearing linearly, right? So we can solve lambda and angular acceleration by a linear solver in this by using these two equations, right? The way that we are doing that in Julia, the way that we are doing this transformation in Julia Sim compiler is that basically in all equation-based modeling frameworks, there is one process in the compilation step that computes the strongly connected components between the equations and the unknowns that are solved by these equations. So for each strongly connected component, we analyze if all these unknown variables appear linearly in all these equations in the same strongly connected component. And if they do, then we simply apply the Turing algorithm in the linear system of equations instead of nonlinear systems of equations. And in here, applying Turing to a larger linear system of equations basically means that the A11 matrix, the A11 submatrix in here is lower triangular. So we want to take advantage of that in solving this this entire system, because we know that A11 is easy to invert. So after doing some linear algebra, we can solve this larger system by doing these smaller steps. And we can see that the only non-trivial linear solve is by this has the same size as the subsystem of A22, because we are computing F2 from A22, right? And this F2 is the only linear solve, non-trivial linear solve in the simplified linear system. And we can see that, as expected, for the last two variables would be the actual algebraic variables that we are solving by this linear solver that is not covered by Turing alone, right? So lambda and the angular acceleration in here are not covered by Turing. And in here in Julia Sim compiler, we can see that we have identified that as a linear system, and we are solving, and we are inserting a linear solve in the right-hand side of the differential equation definition. So we have converted a DAE into ODE. And currently, we are not doing anything special when we are solving the F2 subsystem, the F2 non-trivial subsystem. However, in practice, I have observed that most multi-body systems still have a sparse F2 matrix. For instance, with a 20 pendulum system, we get a matrix with this particular sparsity. And this matrix looks almost like a block-bounded matrix, right? And the future work of modeling toolkit and Julia Sim compiler is to be able to identify this kind of spatial sparsities of the non-trivial linear system, and use a structured linear solver to further accelerate our simulation speed for multi-bodies. And here are two demonstrations of our Julia Sim, our multi-body library developed in Julia Hub. So this is a robotic arm example. Hopefully the video plays. I'll wait for like 10 seconds. If it doesn't, I will just go on. And the equation on the right is a 4-bar linkage example. And the reason that this I'm demonstrating this in particular is that this has a kinematic loop, right? So our multi-body library also handles kinematic loops. Oh, because it doesn't really. Okay, let's try again. Okay, so it doesn't play, but yeah, I will just go on. And another type of system that we are implementing in DigiWell compiler is it's for state machines. They have basically the same semantics as the state machine in Modelica. So we have familiar concepts of instantiating state machines and saying that and declaring that state A and state X are initial states, and we have transitions between the state machines and the conditions for the transitions. And we also have implemented visualizations for the state machines. So on the left is the diagram on the left is the visualization for the state 1 state machine on the right. And we can also simulate that, and after simulation, we will obtain this plot. And that concludes my talk.